This is problem 3. And now we will find the capacitance for a cylindrical capacitor. You have two conducting cylinders. This is cylindrical shell inside and second cylindrical shell. The radius of the inner shell, this is side view. So the radius of the inner shell, let it be A. The radius of the outer shell, let it be B. And I'm looking for the capacitance of this system. And by definition, capacitance is Q divided by delta V, absolute value. So to find the capacitance, I will charge the inner cylinder with charge. I'm giving you lambda this time, where lambda is charge per unit length. And this outer shell will have induced charge minus lambda. So I will have two conducting plates, charge plus lambda and minus lambda, facing each other, two cylinders. And we understand that the electric field, this is again side view, the electric field will be in radial direction. It will be radially out. There is cylindrical symmetry. From symmetry, I immediately understand that. So we follow the same steps as before. This is the expression for the capacitance. Now I need delta V, which means that I need V at B minus V at A. This is equal to minus integral from A to B E dot dr minus integral from A to B ER, because there is electric field is in radial direction. It is ER dr. Now I need to find out the electric field. So to find what is electric field, I will use Gauss's law that tells me that the flux out of closed surface is equal to the charge enclosed by this surface divided by epsilon naught. So which Gaussian surface will we use? We use cylindrical symmetry, which means that my Gaussian surface will be a cylinder located between these cylindrical shells. So this is my Gaussian surface, or if I use the side view, it is right here. We understand that electric field is in the radial direction, so the flux of the electric field out of this cap will be 0, because electric field is in radial direction and this area vector is in horizontal direction. They are perpendicular to each other. Dot product is 0. Flux out of this cap will be 0. What is left is this side surface of the cylinder. And the electric field at each point of this side surface is parallel to ds. So my dot product is just product E times ds. From symmetry, I understand that the electric field is the same at each point of this side surface. I take it out of integral. And integral ds is just s, where s is side surface of the cylinder. Since this cylinder has arbitrary radius r and arbitrary length l, what is this side area, surface area of the cylinder? It is 2 pi r l. And this is the left-hand side of Gauss's law. What is the right-hand side of Gauss's law? 1 over epsilon naught, charge enclosed. Where is the charge? The charge is on the surface. Charge per unit length is given. It is lambda. And length, charge per unit length is lambda, and the length is L. So charge enclosed by this Gaussian surface is lambda times L. L cancels out as expected, and then the electric field between these cylindrical shells is 1 over 2 pi epsilon naught, and then lambda divided by r, and it is radially out. Now I'm ready to find my delta V. It is minus integral from A to B. ER is 1 over 2 pi epsilon naught, and then lambda over r dr. Let's take this integral. I will draw the line here. This is minus, I take constants out of integral, lambda divided by 2 pi epsilon naught, logarithmic function of r, and the limits are from A to B. I plug in the limits, and we have minus lambda over 2 pi epsilon naught, logarithmic function upper limit b minus logarithmic function a, or logarithm b over a. This is delta V. Now I bring it here, so I have Q divided by delta V, absolute value, which is lambda logarithmic function b over a, and here I have 2 pi epsilon naught. Now we need to express Q in terms of lambda, or lambda in terms of Q. Let's express lambda. I gave you lambda, so let's express Q in terms of lambda. What is Q? Q is lambda times the length of the cylinder. So the length of the cylinder, let's provide this length. The length of the cylinder, let it be L capital. Then Q, the charge, is lambda times L, where L is the length of our original of our cylinders. So I have Q, 2 pi epsilon, I'm sorry, we want to express Q. So Q is lambda L, then 2 pi epsilon naught divided by lambda, and then logarithmic function b over a. Lambda and lambda cancel out, and I have 2 pi epsilon naught L divided by logarithmic function b over a. We found the capacitance of a cylindrical capacitor that depends just on geometry, depends on inner radius A, outer radius of outer shell B, and the length of the cylinder. And we again followed the same steps. We wrote the definition of the capacitance, we found delta V, and we found the electric field between these cylinders using Gauss's